So I'll review how to solve the problem starting with number 10. So it says what would be the mass if it had a momentum. So this is the momentum P and this is the velocity V. You know that the momentum equals the mass times the velocity. And so if you're trying to find the mass, you've got to take the momentum divided by the velocity. So your momentum divided by your velocity will find your mass. Okay? On problem number 11, with a basketball and it's moving downwards. So initially the basketball is moving downwards, so its velocity is negative. It hits the ground and then it rebounds upwards. So after the collision, its velocity is positive. You know the change in momentum. We want to know what is the velocity. So here you have to realize that the change in the momentum is mv final minus mv initial. And in this problem, I tell you the change in the momentum. This is how much it changes. That's delta V. You know the mass, so you know the masses. And you know that it's moving downwards with the velocity, so you know the velocity before the collision, right there, V0. So your job is going to be to find the final velocity. So to do that, you're going to take delta V. You've got to add this term to the other side. So you're going to have mv0. That would equal mv final. And if you want to know what v final is, you're going to divide all of this by m. So there's v final. Plug in your numbers, and remember v initial is negative, right? Because it's moving downwards. And that'll give you the answer. Okay, problem number 12. A baseball is moving to the left, it hits a bat, and then it's moving to the right. So here's my baseball. It's moving to the left, it hits a bat, and after hitting the bat, it's moving to the right. Okay? So in this problem, I tell you the mass. So this is the mass. It's approaching the batter at 25 meters per second, moving to the left. So in my case, the velocity initial is negative 25 meters per second, because you know it was going to the left initially. So that's the initial velocity. Afterwards, it has a final speed of that to the right, so the final velocity is positive. In my case, 38. Your numbers are different. And I also tell you the time that the bat exerts a force. 3/100ths of a second is 0.03 seconds. So you're going to take the force times the time equals the change in momentum, and of course that's mv final minus mv initial. Since you know the mass, so I tell you the mass of the baseball, you know the mass, you know the time, and you know the velocity final and the velocity initial, you're solving for f. So to get f by itself, you're going to take mv final minus mv initial and divide it by the time, and you'll get the force F. Okay? Now, we are going to assume that we have the same force down here in the next problem. Okay, so in 12b, you have the same force. So whatever force you got here, you got. And now we're going to do the exact same thing, except we're going to solve this for the final velocity. So we're going to say that the force times the time equals mv final minus mv initial. F we know from the previous problem. T we know because they tell us right here, 0.04 seconds. We know the mass, and we know the initial velocity. It's the same as before. So it says the initial velocity is the same. So you're going to solve this for the final velocity. So bring this to the other side. You're going to have F times delta T plus mv initial. That equals mv final. And then, of course, divide both sides by m to get v final. Okay? And remember that v initial is still a negative value when you plug it in here. Okay? So that's number 12. Number 13, this is a conservation of momentum problem. The student is coasting along a level road. They're holding a backpack. So I've got a student. Maybe they're on a skateboard or something, and they've got a big backpack. Okay? I tell you the masses of the student and the mass of the backpack, and this is the initial velocity of both the student and the backpack because he's holding the backpack. Okay? Now he tosses the backpack forward so that now the final velocity of the backpack is that, what is the final velocity of the boy? So the idea is that the force times the time equals the change in momentum, but there's no external force. So that tells us that the final momentum equals the initial momentum. The final momentum is going to be the mass of the boy. Oops, I got a subscript problem. I'm going to call this the backpack, and I'm going to call this the kid. Okay, so I'm going to use K and B. So we got the mass, the final momentum is the mass of the backpack times the velocity of the backpack final, plus the mass of the kid times the velocity of the kid final. And that's got to equal the initial momentum. Since he's hanging onto his backpack, that's going to be the mass of the backpack plus the mass of the kid times the initial velocity. Okay? And you are trying to find the final velocity of the kid. You're trying to find this thing right here. So you've got to bring this to the other side, so subtract it from both sides, and then divide everything by m to get the final velocity. Okay? Number 14. This one, we just have a bullet slamming into a block of wood. So I'm going to call this my wood. And I've got a bullet zooming along, and the bullet, so this is the bullet, it smacks into the wood, and they fly off. So this is the mass. Make sure you convert it to kilograms. So divide by 1,000. This is the initial velocity of the bullet. Everything's moving to the right, so we don't have to worry about signs. So, hang on one second. So it says the block of wood is stationary, so that means the velocity of the wood initial is 0. It's not moving. So you're going to do the same thing. I'm going to shortcut here. You're going to end up with P final equals P initial. The final momentum is the mass of the wood plus the mass of the bullet, because they're stuck together, times the final velocity. And that equals the mass of the wood times the velocity of the wood initial plus the mass of the block times the velocity of the bullet initial. And of course, the wood is not moving, so this is 0, but anything times by it is also 0. So this term goes away. So what we're going to do is we're going to solve what's left for the final velocity. So the final velocity is going to be the mass of the bullet, velocity of the bullet initial, which are both given in the problem, divided by the combined mass of the wood plus the mass of the bullet. Okay? 14b is a trick question. If momentum is conserved, then if we ask how much does the momentum change, the answer is 0. That's what it means. So how much did we lose? The answer is 0. Okay? To be conserved means momentum doesn't change. All right? Does that make sense? I hope it does. Okay, now, how much energy was lost in the collision? So in this case, you've got to find the initial kinetic energy. So the kinetic energy initial is 1/2. Before the collision, only the bullet was moving. So this is going to be the mass of the bullet times the velocity of the bullet initial squared. That's the initial kinetic energy. The final kinetic energy is going to be 1/2. After the collision, they're stuck together. We're going to have the mass of the bullet plus the mass of the wood times the final velocity squared. Okay? That's how you find the energies. And then to find out how much energy was lost, you're going to take the final energy minus the initial energy, divide it by the initial, and times by 100%. Okay? All right, and number 15 was a challenge problem. If you don't get it, it's okay. What you're going to have to do is use energy. The potential energy of the car at the top of the hill becomes kinetic energy at the bottom of the hill. So you can use energy to figure out how fast it's going to the bottom of the hill. And once you know how fast it's going to the bottom of the hill, you can figure out the collision and how fast they're going after the collision. Okay?